Hi, my name is Bernard Peralt, and I want to talk to you today about the Stokes theorem and basically how it relates to vector fields and how much they circulate or spin around, if you want, and how it relates to the curl of that vector field, which is this funny component that you see right there that you might have seen in electrical engineering or maybe in physics or something like that. So before I get into explaining this, let me just describe what a vector field is. So for example, you have the gravitational field around the Earth. So no matter where you are, you move around the Earth, or even you go up in the air in an airplane, or even you could fly out in space, you still feel some kind of gravitation or a force pulling you down towards the center of the Earth. And you could describe that as some kind of an arrow. So these little blue arrows that you see right there, those would be like a direction and has a certain amplitude, and they could represent, for example, the gravity pulling you down. Or it could be a magnetic field. So you know that, for example, you take a compass out, and no matter where you move around, the compass always sort of points north. So the little compass arrow might be this little arrow right there, pointing in a certain direction. So a field is something that's three-dimensional. So in other words, these arrows, these little pointers, if you want, exist everywhere in space, and each point in space has an arrow that has three different components. So there is a component in the x direction, y, and z direction. So it can point any direction in three dimensions. So that's why I'm saying that the field, the overall field, can be represented as some kind of a function, and it exists at every point in space, and it has three components. There's a component for each direction. So for example, in the x direction, the y, or the z direction. And and then these fields could be sort of like constant, like this one. So the arrows are all pointing in the same direction, same amplitude, no matter where you are. Or you can look at this one, and this is more like gravity here. Everything points towards the center right there. Or it could point out. The arrows could be in the opposite direction, for example. So if you have electric charge and you look at the electric field, it emanates right from the charge that could be in the middle. And there's a sister theorem to the Stokes theorem that's called the Divergence Theorem. Now, sometimes what happens is that the fields sort of like circulate like this, a little bit like a vortex, like a tornado, if you want, right? So they circulate like this. And this is what this video is about. It's about that the amount of circulation and how it relates to circulation at every point, and you add up all the small circulation and you get the larger total sum of circulation. So when you look here, for example, I mentioned divergence and circulation. So when you have, for example, in the middle, some kind of a field source, if you want, and that source could be a mass creating gravity. In this case, the arrows would be pointing inwards. It could be a charge, and then you would have like electric charge, and you would have electric field radiating out of that source. So you have some kind of a radial source, and it generates this field here. And these arrows are not just in there, but they keep going out, and maybe as you go further out, they're smaller in magnitude, but always sort of radiating out. This could be like, for example, a light bulb in the middle, shining light in every direction. The amount of light it produces, right, the number of photons it produces at the source can be somehow captured in an enveloping. So some you put a surface, or you wrap around something around the light bulb, and you capture all these photons. And the further out you go, the less the intensity, but you still capture the same amount of photons. And that has to do with divergence. And that's going to be maybe a sister video I'm going to do at some point. So this is not what I'm going to be talking about here. So I'm going to be talking today about the amount of circulation. So imagine that you have again a vector field and it goes around and circle like this, right? And then somewhere, and the reason for that is somewhere in the middle right there, there's like some kind of little spinner. And that little spinner sort of generates this vortex, if you want, and it makes things circulate around. So if I take a certain path around here, right, a circular path around here, I see that, you know, the vector field, right, sort of all points in the direction of the path, and it circulates and sort of makes things spin around. So speaking of path and path integral, let me describe what a path integral is, and then we'll move on with the circulation. So again, in blue, you have these different field arrows, if you want, and you describe a path that goes from point A right there to point B, and you have an arbitrary path that I've just drawn right there, right? And what the path integral is, or the line integral along the path is, imagine the projection of each one of these vectors. So this is the projection along the path, and this is the projection along the path right there. So of course, if the vector field is perpendicular to the path, then it doesn't have any, it's got zero projection. If it's 100% in line with the path, then it projects 100%. But if it's somewhat 45 degrees, then somehow, you know, 0.7 of it will project in the path. So the path integral is the sum of all these arrows times the small amount of distance that you do across the path from A to B. So, and it's defined as a sum. This is in calculus, we say it's a sum from point A to point B of the projection of the path across the small line, and you add all these up and you get the path integral. So when we talk about circulation, what we're going to do is do something similar, except that we're going to go back to the same original point. So we're going to follow a path from point A to point B, as you see right there. And once you reach point B, you're going to go back and back to point A, and not necessarily going back, reverting your path, but you're just going to keep going and then going back to A. And that's why we say that this is like a closed loop line integral, if you want. So that little closed loop arrow and following in the counterclockwise direction of the vector field along this particular path. And this path could be circular, could be a square, as long as it's some kind of a closed loop, if you want, and it's a continuous path. And we define this, or I define this as somehow the circulation around this path. So one of the interesting property about circulation, or a closed loop path integral that we just seen, is that if you break the path into different portion or different segments, the circulation of the overall is overall surface is the sum of the circulation of all the different parts that you broke apart, and that's shown right here, for example. So as you can see right here, I'm not showing the blue vector field in the background, but of course it's always there because that's what we're measuring, the projection of those. But if you look at this overall path, like the red path around, right, and you calculate the circulation there, you'll notice that it's equal to the circulation here. So I broke it in half right there, and I calculate the circulation C1 right there, here, and that would be like somehow maybe half the path. It doesn't have to be cut exactly in half, and plus the circulation of the second half. And the reason for that, and you can see this, is that in the middle right there, right, you notice that as you're going up this way, right, and you're going down in the other direction, so the C1 plus C2 cancels out along the dividing line right there, as if it's because they cancel each other out. It's the same. The vector field is the same, and you calculate it once in one direction, and you calculate it once in the opposite direction, and therefore it cancels out. So when you're adding up C1 and C2 there, right? Notice that you're canceling this, and therefore the purple and the yellow arrow adds up to the red one, right? And that's what's shown down here. So what I'm showing down here is right there that the circulation along the red path, right? So this is a red path of this force field or the vector field is equal to the sum of the two circulations for the yellow one right there and the circulation for the purple one. And what's kind of interesting is that I could have divided this into more smaller segment like that and break it up like that. And the total circulation would be equal to the sum of all the different smaller circulations right here. So that's, I think, is the fundamental property of circulation. And it's very convenient because what we're going to end up doing is we're going to end up breaking down calculating the circulation for an infinite small number of small little components, and we're going to add them all up, and then we could use calculus to do this. So again, that's shown right here, for example, in Cartesian coordinate. If I wanted to calculate the circulation around this path right there, right, and looks kind of squarish, but in fact it's only squarish because we're sort of zoomed in right now. So that again is circulation around of the vector field around this is equal to the sum of all these little circulations that you have. And we're going to make these smaller areas like a dx dy infinitesimally small, and we're going to add an infinite sum. And that's the whole thing about calculus. That's the magic of calculus. And the reason why that is if you look, is that between C1 and C2, these two right here will cancel out. So will these one, because it goes up and then it goes down. So these cancel out. So all of the, if you want, interconnect between those small surfaces all cancel out. And the only thing left for the sum of all these smaller circulation is the total circulation all the way around. So because there's nothing canceling this arrow, nothing canceling this one. So effectively by adding up the circulation of all the smaller components in the complete surface, you can't miss any, you can't have a gap, then it's equal to the overall circulation. That's what's shown right there. So the total circulation is the sum of all the smaller circulations right there. All right, so that here is the key thing. And so going back to the original problem, and as if I want to calculate the circulation of any path, and the path shown here in red, for example, right, this big path around here in red, and that's what's shown right there, is that the circulation of the force or the vector field across this red path, right, that will be the sum, right? So that's the sum of all of the smaller circulation of these little smaller dx dy. And then what we're going to first do is see if we can calculate the circulation for each one of these little square right there and shrink them down to a point, and then do the infinite sum of all these circulation to calculate the overall path integral or circulation around the entire path. So that's what we're going to do next. So what we're going to do next is calculate the path integral or the circulation for one of these very small surface right there, right? A very small surface right here, and add them all up, and it's going to give us the circulation for the red path right there. So zooming into one of those small surface at a point x, let's say point xy right there, X and Y, so that point right here. And what we're going to do is look at the projection of that vector field along the x-axis and move by a small dx amount, move up by a dy amount, and then backtrack if you want, move back into small dx and back down to make a closed loop integral. So what we're looking at here is the projection of this blue vector field along the x-axis. So let me just show you what that looks like. So imagine here that you have a certain vector and it points in this direction, and you look at the projection along the x-axis, and let's call that F1. So it's F1 in the dx direction, let's say F2 in the dy direction, F3 in the negative dx direction, and F4 and going down. So adding all of those four projection, if you want, or path integral of the four paths. So the circulation for that small dx dy is F1 dx plus F2, and the negative sign here comes from the fact that dx is negative, and negative sign for negative dy. So regrouping the terms in the x and the y direction, what you see is basically what you have is in the x direction, you have the difference between F3 and F1, and in the y direction, it's a difference between F2 and F4. And that's pretty obvious right there, is that if F3 and F1 are identical, then they cancel each other out and it goes to zero. But if there's a small difference between F3 and F1, then that difference is what's calculated right there. And same thing in the y direction. So it's the delta and of the field, if you want, and the x, and the delta and the y. And the way we do a delta fx here is by looking at the rate of change of the vector field in the x direction, and it's that rate of change with respect to y, because it's between F1 and F3, we've moved up dy, and the rate of change of the vector field in the x direction, and the rate of change is the partial derivative with respect to dy times a displacement. So this is how you calculate the delta fx, and in a similar way, this is how you calculate the delta fy, and you substitute this back into this equation right up here, and you end up with the circulation in the small dx dy area as the rate of change with respect to y times dy dx, and the rate of change in the y direction times, again, dx dy as well. And if you want, you can regroup this and move this to the left and divide by dx dy, and you end up with this right here. And you define this right here as being the curl of the vector field, right? So define this as the curl. So the curl of the vector field is the partial derivative of fy over dx minus the partial derivative of fx over dy, and you define this as the curl. But notice that the curl is also defined as the circulation over dx dy per unit surface, right? So you can rewrite this using saying that the circulation on that small dx dy square is the curl of the vector field times dx dy, right? And curl is sometimes also written using this notation right here, and using the del operator, and it's a del cross f. We'll maybe get back to that at some other point. But what we were looking for initially, if you remember, was how much did the field circulate in a very, very small point, right? So almost like a dx dy small point. And it turns out that it's the curl times dx dy. And the next step is to calculate how much does it circulate around the larger path, if you want. So what we did so far was to calculate the circulation for one little dx dy, and we're going to add them all up to calculate the bigger circulation around the bigger red path right there. And so that's the next step right down here. and it turns out that if you calculate the circulation around the bigger line or the bigger path around the surface, then it's the sum of all these smaller circulation, and the sum being like a double surface integral of the curl times dx dy, and that happens to be Stokes theorem. But the key here is to remember that the curl, right, is defined as the circulation per unit surface at a small point. And if you remember this here, right here, that's all you need to remember. If you remember this, and you remember that all you need to do is add them all up over a surface, then you remember Stokes theorem, and it's going to make everything about the curl far more intuitive. So you're going to be, and we'll use an example here with Maxwell's equation next. Okay, now let's take a look at the Maxwell's equation. So Maxwell, maybe a century ago or something like that, managed to reduce everything about electricity, about magnetism, about electrical induction, motors, power generation, electric power generation, generators, and so on, into four fundamental equations. And here they are. And the four fundamental equations show how electric and magnetic field behave and how you can predict them using these equations. So two of the equations actually involve what's called divergence. This is electric field right here. This is magnetic field, and this is a divergence. And what we've shown you earlier was circulation of the electric and the magnetic field. So if you remember earlier, we explained that divergence is like there's like some kind of a point charge or some kind of a source somewhere, and somehow radiates out of this source, like an electric field, for example, or this could be a mass, and you would have gravity pointing towards the charge. So, and if there's a positive point charge, there's electric field radiating out, and if it's a opposite charge, then the arrow points in the other direction. So this is divergence, but that's not what we covered here. What we covered here was curl and circulation. So the other property of these fields is that there are sources of circulation, as you see right here in the middle. And once you have a certain amount of circulation source, what you have is it doesn't matter how far out you go. What we've shown is that the circulation of a path, right, outside is a sum of the circulation of everything inside. Right, in this case, you have a single circulation source right there. And if you look here at the two of the Maxwell equation that actually relate with curl and circulation, they're right here. So it says here that the circulation of the electric field is the rate of change of the magnetic field over time, and something similar with the magnetic field, it's also the rate of change of the electric field over time. Plus the other thing that gets added, plus the amount of current flowing through the surface that's around the path that you're calculating circulation around. If you look at the electrostatic case, so static here meaning that it doesn't vary with time. So this equation, the rate of change of a magnetic field goes to zero. The electric variation goes to zero, and these equations actually simplify in that the curl of the electric field is zero, and that turns out to be a conservative field, but that's a different video. And the curl of the magnetic field is equal to the current density, right? So going back to the definition, if you remember how we defined the curl, I said the curl is the amount of circulation point in a point. It's a circulation density at one specific point. And what this says is that this is equal to the current density, right? So the amount of flow of charges, right? So one way you can get the current, you get current flowing into a wire. So here's a wire right here, for example, right? And you have like charges in the wire and that flow inside the wire. And what we've seen before is that, it creates a magnetic field around the wire. So if you were to put a compass around a DC wire, then you'll see that the compass arrow will align with the magnetic field. So that field exists everywhere, not just here, but exists everywhere outside the wire. And as you move away from the wire, it actually, decreases in intensity. So if I were to show this, for example, with the wire pointing up towards the screen, right? So it'd be the wire would be like sort of like going through a sheet of paper and aiming up to your eyes. So this is the way right here. This would be like the wire right there in the middle. And what Maxwell equation is saying is that the if you have a certain amount of current there, it actually generates a certain amount of circulation. So, so it says here that the curl, in other words, the circulation, the point circulation per unit surface right there is equal to the current density. So if the circulation density is equal to the current density, that means that the circulation is equal to the current times constant, right? So it's proportional to it times a constant. So that acts like a some kind of like a spinning source. Think of it like a little paddle wheel, sort of like pushing things around this way. So, and if you remember what we looked at in the Stokes theorem was saying that no matter where, if you create a path like this, for example, right, and you calculate the amount of circulation in the larger path, it's the sum of the circulation everywhere. But the circulation is equal to zero everywhere except where you have a source of current. In this case, there's only a source of current right on this little wire right there with charges sort of coming up, right? So the amount of circulation that you have here, right, is equal to the sum, the circulation that you have, no matter how far you are. So if I do the circulation on this path, path 1 right there, or if I do the circulation on path 2 right there, they're the same. So for the circulation to be the same, that means that the magnetic field here, so the magnetic field here has got to be smaller than there. And the reason for that is you're adding up a certain larger amount of magnetic field right here, but over a shorter distance, because this is a smaller circle if you want. So as you're moving away from the wire, right, so the amount of circulation is the same. So that means that the electric, or sorry, the magnetic field has to be smaller because you're adding up smaller arrows over a much larger radius, right? And in fact, if you were to add up like 2 pi r is the distance here around, so this is a circumference of that path, times the magnetic field is equal to mu times I, which is a current, right? So in other words, the magnetic field is equals to mu I divided by 2 pi r. So that derivates directly from Maxwell's equation right there, saying that, a certain amount of current generates a circulation, and that circulation is going to be the same no matter how far we go. So as we're going further and further away from the wire, then the magnetic field decreases with 1 over r, so it decreases proportionally with the radius, right? The other thing about Maxwell's equation is that it's linear. What does that mean? That means that if you double the current, so if this current coming up here is twice as much, then the magnetic field everywhere in this field is going to be twice as high. The other thing is what you could do is you could take the wire, have it go through that sheet of paper coming up, and then you sort of wrap it around, and then you make it come back up many, many times, and you can like have it come up here, have it come up there, come up here, and then you just have, let's say, for example, like n times the wire coming back up, so creating a loop of wires, if you want. And in this case, what you realize is that the amount of circulation is just n times, so how many winding you have in that wire. So it's going to be n times, so you could add an n right there, n times the number of wires. And the other thing you can do is eventually the wire has to come down somewhere, right? So let's say the wire comes up here, and it comes down right there. So the wire going down into the sheet of paper is actually also a source of circulation, right? Except it would circulate the other way around because the current would flow down and the circulation would be in this direction right there. So the wire coming up circulates this way, and the wire going down circulates the other way around. So if you're standing far away from this loop of current, then what you have is you have something eventually from these wires coming down, and you have something from these wires going up, and they sort of cancel each other. Except that right here in the middle, what you have is you have a certain electromagnetic field going down in this direction, and then it going down in that direction from the wire going down. So they add up each other. And that's the principle of electromagnets, right? So right down here in the middle, you have like equivalent of electromagnet. So I'm not going to go into other examples, but hopefully gives you an idea that when you're looking at the curl here, and you have to think about circulation. And when you're looking at curl, then you have certain sources of circulation. And that's what Maxwell's equation says right here, is that the current is actually some kind of a source of circulation, the same way as an electric charge in divergence, for example, is a source of electrical radiation. All right, so thank you for watching. Hopefully you enjoyed this video.